Tonight on Rubber Duck Engineering, we will implement malloc. Malloc. Hey, Eric, how are you?
I'm good. I'm in week 5, 6 of vacation. It's pretty lovely.
But who's counting?
I'm kind of counting because I'm only giving myself a few more before I figure out what's next. But I'm enjoying golfing and reading books, and it's good times. So
I once went to a driving range. I tried to hit the golf ball as hard as I could, and they had these different little like cones out in the field, and I didn't even get to the first cone. It was embarrassing.
The secret, it turns out, is not to try and hit it as hard as you can.
That is really the opposite of what I tried. Is there like a technique or form that's important?
I golfed some as a kid, and I hadn't golfed in probably 10 years, but I had started golfing again with my dad over vacation. So, but yes, as you said, tonight we're doing malloc.
Malloc. What is malloc, Eric?
What is malloc?
What does the viewers want to know?
Allocation. Couple times in my career.
Oh, that makes sense. I never realized it stood for anything. It's always just been malloc to me.
Yeah, it's memory alloc.
Okay, that makes sense. What like other kind? I guess there's alloc for file alloc.
There's calloc, which is the clearing allocator, and there's realloc, I think.
Realloc. What shouldn't be re-malloc? If you're I don't know. The names don't make sense.
I don't know. Maybe malloc does not stand for memory allocator, and I just interpreted it wrong in my brain.
No, it makes too much sense. It must be true.
But I think I've worked on malloc a couple times. My first time was my first job at Apple, and it was just like updating to the latest BSD copy of yada yada or whatever. And then the second time was when I was working on Safari. They switched from TC alloc to J alloc or something like that, like maybe some JE other implementation of alloc. What'd you say?
Maybe JE alloc. JE alloc's a famous implementation.
And then they switched again. Like the Chrome team, I remember, switched again the underlying WebKit allocator, which was pluggable at this point.
But I mean, this is a big strength of malloc. Like the API contract for malloc is very, very simple. But like the amount of different approaches you can take and the different effects that those have has a huge effect on your program.
Yes.
Because most programs are just constantly allocating and deallocating memory.
Yep. And so I guess we'll probably get to some of that, although maybe this is going to be a multi-episode malloc series or something. Because I think we can probably get a very basic malloc working tonight. Maybe we can even, I bet you could replace malloc. Although ours will not be probably worthy of doing that for the C library.
Well, why don't we try to write a basic one, and then maybe we can futz around with seeing if we can run a real program using it as the malloc.
I mean, that is the goal. So to the code machine?
To the code machine.
That needs to be a t-shirt, by the way. So yes, I this afternoon, just to make sure that my Ubuntu setup on my Windows worked, I have this simple malloc. I've confirmed that I have a working copy of Clang. That's the C language front end to LLVM that can compile this C program and run it.
We have an off-topic question. How does a Dart compiler handle recursive functions in compilation? I have no idea. Do you know, Eric?
No. If I had been in charge of the Dart team longer, maybe I would have learned, but no.
We had a whole team for that. They were amazing at it. I never questioned how they did recursive functions. Basic malloc is easy. It's free. That's tricky. Yeah. I see what you're going for there, James.
I mean, the like dumbest. Well,
we should write the contract. Right? What is the contract for malloc? Right.
Yep. Void star size T. Yep.
And then there's free.
And we should maybe explain what this is. So void star is an untyped pointer. It's like we have no idea how big the thing that this is pointing to is. It might be 8 bytes wide. It might be who knows long. And then this size T is this is unsigned. It's not the size of a pointer. What is the contract on size T?
Unsigned value that's as big as the largest possible buffer. So in 64-bit land, it's 64 bits. In 32-bit land, it's 32 bits. We should probably prefix this because we don't want to actually collide with the real symbols.
Okay.
And what this is supposed to do is go find you some memory. Like it's supposed to return a pointer where the client or the caller is allowed to use this much memory starting at this address.
Correct. It will be at least that large.
Yes.
And this will return 0 on failure.
Yes. That's a whole. We can dive into that subtopic.
And this thing is 0 allowed?
0 is allowed. Yep. 0 is not an error to pass to free.
Okay.
What this is supposed to do is
nominally frees the. It says I'm done with this region.
What is free? What does that mean? So it just means, I don't know, like maybe use this for something else. Like it's got a very nebulous contract.
Well, it says I'm done. It says I won't touch this anymore.
It's like a promise. Like the caller promises not to touch the thing that this pointer points to anymore. And then the system can do whatever it wants with it. It might reuse it. It might do nothing with it. It's up to the implementation.
Well, and that's important because, like, if you swap in something like guard malloc, it will yell at you if you touch the memory after free. Like it'll null out the memory, or it'll make the page. It'll give every allocation its own page and make that page non-writable afterwards. You were saying?
Yeah, I don't know if we'll get to these other two, but these other two
are these actually part of the contract? I know. I think calloc is. I'm not sure realloc is.
Realloc has to be because so let's just say what they are, right? So calloc is the same as malloc, except it promises that the memory returned is always 0. And the reason this is important is it's often the allocator can ensure that property more efficiently than actually going through and zeroing out all the memory. When malloc returns a pointer, it makes no promises about what values are already there in memory.
Yep. It also makes no promises about alignment or anything like that.
Malloc, I'm not sure about that. This might actually have an alignment. It may. We might want to look that up.
I expect various different mallocs might make that promise, but I think the generic contract does not.
I see.
I don't know.
And then realloc is a very funny one. So it says, this is a pointer that was previously returned by malloc. And now I wish that instead of the size that I had passed to malloc the first time, I wish that I had passed this size to malloc. And so this will either just return back the same pointer and be like, okay, you can now use that amount of size at this address, or it will go return you a different pointer and do the work of copying over whatever was pointed here, whatever was in memory here to the new location.
And remind me why this is needed.
Because it's a thing that you can't do from outside. Like, so it's very common that when you call malloc, you actually get like a thing like this. It says, here's my actual memory that I promised you, and then here's a bunch of extra space that is available. But from the caller's point of view, you don't know. And so let's say you want to make your thing slightly bigger. It's possible that the implementation could just leave it in place and switch these from X's to Y, so give it to you. But there's no way from outside the contract to know that. But it's always a correct implementation of realloc to just allocate a new thing and copy the stuff over.
Well, I guess I'm a little skeptical that it exists only for that optimization. Are there no things that you can't do?
It looks like the contract for calloc slightly wrong.
Oh, what's the two size T's?
You just multiply them together. I think we'll do these later. Like let's focus in on these two, which are the main important ones.
Yeah, so we could write like the the very simplest. Are we doing it here, or is this in the header?
Well, let's just do it here.
So like the very simplest, gets a page from the system.
Mm-hmm.
Get the block from the system, right? A block of memory from the system, and hands you back a pointer to the space of that block.
Yep. So how do we get
a terribly inefficient malloc?
Well, I think it's a good place to start, like in the sense of like build the dumbest one and iterate, right?
Yep.
So how do we get a block of memory from the system?
And the simplest does nothing, right? But it could also return the block to the system. Mm-hmm. How do you get a block from the system? That's a syscall, which I don't know what they are on Linux.
Are we assuming Burk or map? Good question. We're on Linux, so we're going to use mmap to do this. I think if we try to use Burk, we might be fighting with something else, like the real malloc in our process or something.
What is Burk and map? My malloc knowledge is all from Mac.
Burk. Okay, so Burk is like a super old thing. So in I don't know what ancient version of Unix or POSIX or whatever, there was the program break, which was I loaded your program into memory because of course it was one image and it didn't consist of any shared libraries or anything. Okay. And then there was the space right after that. And so there's a syscall called sburk, which allows you to basically start reserving linear addresses starting right after your code segment, and then give those to you as mutable addresses. And so, like if you run glibc, for example, sburk or Burk is one of the very first syscalls that it emits to try to get some space to work with. But be that as it may, I think we should use mmap.
Okay. Okay. How do I pull up? Why is this not?
Here's the mmap contract.
Oh, maybe we don't have. Maybe I don't have my syspath set up correctly.
Mmap is like this Swiss Army knife function that does a million billion things. But let's write a function called pagealloc. We're going to need this in all of our versions. While it helpfully builds in the right arguments. So what are we doing? We're saying we don't have an address in mind. So that's the first argument. We have a particular size that we want, which is the page size. Mm-hmm. We would like to be able to read and write the memory that we get back. This mapping is private to our program. It's not going to be shared with another program. And it's anonymous, so meaning it doesn't come from a file. And so we're asking the kernel to please supply anonymous memory, where anonymous memory in this case is basically zeros. And then we pass -1 as the file descriptor. And then since we're not passing a file, it doesn't make sense to say what offset in the file we want. And then this thing returns a very funny value. I think this is like -1, or I forget exactly what value map failed has, but it's some crazy value. So we translate that into null, and then we return the pointer.
This is bananas. It's bananas just because it's like this is not the API you would design for this in 2022.
No, and so like you could look at someone who designed an operating system in the past few years. You can look at what API they designed for this. Vastly simpler, but it doesn't matter. This is the magic incantation to allocate pages.
On Linux.
On Linux. And on Windows, it's actually simpler too. They have a function called virtual alloc that does the same sort of thing.
Okay.
So some interesting facts about what's happening here. I don't believe on Linux that this will ever happen. Linux is a system that overcommits. And so when you say mmap, this doesn't actually go and get any memory for you. It just says, okay, I've sucked up these addresses in your process. Mm-hmm. Maybe this could fail if you literally run out of address space. Sure. But I think as long as you have a contiguous region of this size in your address space, I believe this will succeed. And if you don't have enough memory in your computer, when you start interacting with the memory pointed to here, that's when bad things will start to happen. Either your program will get killed, some other program will get killed to make memory for you. So something interesting will happen.
This overcommitting behavior actually came up for Dart, since someone was asking Dart questions earlier. Recently on iOS, because I guess iOS maybe doesn't over. Well, anyways, the behavior that was desired. This was for like compacting pointers.
Mhm.
We were calling and asking for like a 4 gigabyte block or something like that. And then on other systems, they would just say, "Sure, here you go," and wouldn't actually do anything. And iOS instead would just be like, "No, sorry, crash."
Yeah, so for example, on Fuchsia, every Fuchsia process when it boots up just asks for 1 terabyte, please. And we're like, okay, we don't have anywhere near a terabyte, but sure.
Why does it ask for a terabyte?
Just because it makes things simpler, because then you reserve 1 terabyte of your address space for your heap, and then you can manage your heap just in that terabyte. And we don't really have any programs that use more than a terabyte of memory because we have like we don't have that much memory right now.
Huh.
So that'd be another way of
that, but maybe not for now. Go ahead.
Yeah, so like let's build this simple malloc, and then we'll think about how we're going to tech up our malloc. Sure. We may end up with a strategy where we just reserve a terabyte, but we don't have to.
And so this is in bytes, this size?
That is in bytes. It may need to be a multiple of page size, though.
I would expect so.
I'm reading the man page. The length argument specifies the length of the mapping, which must be greater than 0.
Mm-hmm.
It doesn't say anything about having to be
if size less than or equal to 0. I don't know.
It doesn't say it has to be a multiple of page size, so maybe it doesn't.
So then it must round up to the nearest page size.
Less than or equal to 0.
So
yeah, so it's always going to, well, yeah, the mappings are always going to be page aligned. So this pointer will always be page aligned that you get back.
And for those watching, like a page of memory, let's see, test my knowledge here. The OS gives you back, I think it's in order to like save bits in the like memory mapper or the memory allocator or whatever. They chop off the low bits, and that's the minimum page size.
Yeah. So your process, the kernel's keeping track of all the addresses in your process. You can think of it in some sort of like tree-like data structure, some sort of sparse representation of what is it assigned to each address in your data structure in your process. And those data structures can get very complicated. And so the kernel simplifies things by not reasoning byte by byte, but reasoning in chunks called pages. And so you can think of a typical page size as like 4 kilobytes. Yep. Is very common. But on modern systems, you can have 8 megabyte pages, or like it's actually starting to become pretty variable. As people have really huge amounts of memory that they want to deal with, they start wanting to deal with it in bigger chunks.
And there's a similar concept on the file system side, where those are the block size of the file system, which is the smallest file you can have. Right? You can't have a file smaller than the block size. So if the block size is 4 kilobytes, the smallest file is 4 kilobytes. Your OS may actually show you a smaller number by computing the actual size, but you've actually allocated that much of physical space.
Yeah, so I think what we're getting at is here the dumbest. The dumbest malloc would just return, make an entire mapping for every allocation. This would be horrendously slow, and your program would die. And then if you were done with the pointer, you would call unmap your pointer.
Okay.
0 here.
I'm trying to think if there's like a good way for us to test this.
So this is an interesting thing. So when you pass unmap, you have to say how much. You'll notice here we had a size that we allocated, and then we forgot it. So already we have problems.
Okay, well, I guess we're keeping then a list.
Yeah. So
now we have like static allocated pages. Allocated pages. I don't know. How do you even do that in?
Yeah. So let's start simpler, right? So let's think about we're going to want to have a struct that is Copilot. Called a block. Let's call this a pool. Okay. have.
So it's a doubly linked list. Why?
Because we're going to keep track of, like, we're going to end up calling page alloc a few times, like as we need more and more space, and we need to keep track of them. And we have to basically keep track of them in fixed space. So you end up using tons of linked lists in an allocator. But maybe why don't we start even simpler? Let's just start with just a single pool. So let's start with this, just single pool. It's going to have a start pointer, and it's going to have a size. Okay, and then we're going to have a global static.
So this is we're allowed to call page alloc once, basically?
Yeah. And we're going to initialize this to null.
Okay.
So the first thing we need to say is if we don't have a global pool yet, then page alloc, I don't know, let's page alloc 10 megabytes. So our total heap is only ever going to be 10 megabytes big.
And then we're just going to return the front of that pool, or?
So now we need to think of, like, what we need, like a header. So we need to keep track of, like, what parts of this pool have we given out so far. So we're going to need a struct that's we're going to need a thing in the pool, which is the free list. Struct free node.
We're making a bunch of choices now in our malloc.
Yep.
So you're going to instead alloc you're going to over alloc every call and reserve a header before the pointer for these this information. Is that where you're going with this?
I'm not sure. We can keep following our nose and see where we get to. Our free list is going to have basically be a singly linked list, and in each node of the list, we're going to keep track of how much memory there is available here. So when we initialize our pool, we're going to set the here. We're going to set the free list
to the start.
To be the start.
Inside.
Then we need to actually initialize this. So we're going to say the free list next is null, and the free list size is pool size. So there's something very important that's happening here, which is we're writing in C, and that is essential right now.
Why?
So if we, so this thing that we just did here, we're going to have to do a cast. But
yeah, because C++ would try to use space before your pointer for you.
Right. So in C++, so we just basically, like, we got this void pointer back from the OS that had no object representation of it. And we just hallucinated the fact that it was a free list, a free node.
Yep.
And so that's fine in C. C says that's a totally legit thing to do. In C++, we would have to do something a little fancier. We would have to basically start the lifecycle of this object, which you can do using a thing called placement new. But I don't want to get into that. But we're working in C, and that's important for what's happening.
Okay. Yeah. Okay. So, all right. So we've made our. Hold on. So we made our pool, and then we made a single free node, the whole size of the pool, and then the way we're going to do allocation is we're just going to move the start by that size. Then fixing up free will be a little different. Okay.
So we're going to start with taking the free list. And we're going to say, the dumbest thing that we could possibly do is say, while current arrow size is less than the size. So we're going to walk through the free list until we find a thing that is like, we'll find the first free node that could possibly fit the thing that we want to fit.
Yep.
Okay.
This is less than or.
If it was equal.
You're right.
Yeah. So we're going to need a thing. This is not going to be quite right. We'll come back and have to fix this when we do free, but we'll start now because we're going to need the space for the size that the client wants, plus a little header that we'll get to in a second. Okay.
I mean, we could just, Yep. Mm-hmm.
So now, if current size is less than size, return null.
Yeah, I'm going to over-engineer your.
Yeah. We do account for header. Allocation header.
If current size. Well.
Okay. So now current is what we want. So for now, the returned address that we're going to return is going to be current.
What?
Now we need to.
Why is this needed?
Why is that needed? That's not needed.
Okay.
Okay, so now we're going to fix up this. Oh, we did this backwards, actually. This is going to be, so we shrink the size of the free list entry, and then we sent current equals current current plus size. But we haven't handled the case where size is now 0. What we've done is we've shrunk the size of the.
I see. Yes.
This is probably not the best way of doing it, but we'll start here. Okay.
I mean, what the Copilot code earlier was alluding to was the idea that you could just wrap every single space in your free list and your allocated list are the same.
Mm-hmm.
And there's just some sort of flag, whether it's free or not. I don't know if it's a good idea, but that would be possible.
Yeah, so we could do something like that.
I think our direction is fine.
Yeah, so our alignment is also off here. Like we're getting sort of weird alignments out of things. We're also allocating from the back. Basically, we're allocating from the back of the free pool, the free list entry.
Why? Current size. Oh, I see. Why don't we break when? Okay, yeah, we're allocating. The back allocation is just coming from this here, that we're not exiting once we find the first one.
Why don't we do next and previous? Let's make it a doubly linked list. I think that will make our life easier.
Okay.
Let's try to do this. So
I think our life would be fine if we allocated from the front and we just did a single link, but that's fine.
So let's handle the case where the free list node goes away, which I think is interesting. So we want to say, basically, if the current size is less than the needed size plus the size of the free node, right? We have to remove the free node from the list. Otherwise, what we're going to do is we're going to split the free node. The way we're going to split the free node, if you scroll down a little bit, I think splitting the free node is the easier case. So in this world, the pointer we return is going to be the address of the free node. Okay. we're going to make a new node. Maybe it's conceptually easier to make the new node first. New free node. Current plus this size.
Is that always true? This is not the this is assuming there's still space in the free node.
Right. That's why we have this case here.
Okay.
Okay. So now the free nodes next is what it was before. The free nodes previous is what it was before. And the free node size is the shrunken size. And now we need to update basically next previous here. And previous next. If there's a next one, we have to update it to point to the new location. And if there's a previous one, we have to update it to point to the new location. Otherwise, we need to update full free list. If there's no
this code is so hard to read.
Yeah, it's sort of a function of it being in C.
Okay. Yeah, I don't think this double link is actually necessary, but because we could also have just saved off the previous when we were walking.
Do you want to do it that way? Okay, we could do it that way.
Because we only ever need it for that, I think.
Okay, so let's go back to a single linked list. So when we initialize current, we'll set previous to null. And then whenever we advance, we will set previous to current and then advance.
So are you still intentionally returning the last one instead of the first one?
Still intentionally returning the last one instead of the first one.
Right, so while size is less than.
Oops.
Oops, sorry. But like, don't you want while current size. Oh, this is less than. Yeah, okay, never mind. Yep, no, this is fine.
So if current, if previous bang equals null, then yep, like that.
Okay, so now we take current size. So this is like needed for split.
Okay. Now if we need to remove this free node, then what we need to do is we're still going to return current, but we're going to say okay, and so then here we also need to check if current is null. No for all.
Does C just always end up subtle? It's been so long since I've written C.
Yeah, especially when you're dealing with like linked lists and stuff like this. It always becomes this sort of like soup of complicated cases because you don't have any abstraction to help you with.
Yeah.
The back is linked for compaction. Yeah, we'll run into that problem when we do free. We won't be able to like join nodes in the free list, but we'll get there. Yeah.
Okay.
Okay. So now I think we should do free, which will now bring up an interesting point.
Okay. I also wrote down this case, which I don't know if it matters.
Case where the free node is bigger than was asked for, but not big enough to split.
Right. So if you, because we tested against a different size here, right? It's needed size plus size of free node. So you can end up in a case where it's not big enough to split.
Mm-hmm.
Let's see. So,
right. So you get some extra. There'll be extra memory given to the program that it doesn't know that it can use. Yeah, this is very common in allocators, which is why realloc is a thing.
Well, but
we're missing a bunch of alignment code here, by the way, too. We're giving out very very unaligned pointers, and so we probably have to pad a bunch of stuff with a bunch of alignment things.
Okay. Okay.
Should we do free?
Yep. Yeah. I feel like we sort of like did like one strand of complication without, recognize the other 3 strands that we need to worry about here. But
okay. Yeah. Do you want to talk about that?
No, I think our approach is fine. Let's keep going.
Okay.
All right, so let's see. It's free. We need to.
So there's a missing piece of the puzzle that we don't have.
Yeah. And where the free node would go in the free list. Make a new node. What's the missing piece of the puzzle?
The missing piece of the puzzle is a sort of size information. Like we don't know how much memory was allocated at this location, which is going to be an important piece of information.
I see, because of the free list will need it too.
Yeah, let's say we want to create a free node at this location. We wouldn't know what the size is.
Mm-hmm.
So we can just try to do that, right? We can say, okay, reinterpret this pointer as a free list node.
But we don't know what to set as the size.
We can set we can fill out the rest of it, right? We can say node next is going to be the pool free list, and the pool free list is going to be the node, right? But we're missing node arrow size.
We could make our lives simpler, though, to go with Copilot, where Copilot was going, where you just make all allocations have a header.
Mm-hmm. Yep. So we should definitely do that. So let's make an allocation header.
And then your free list and your allocation list are the same. And then all you have to do is you mark this thing as no longer being allocated, but rather being freed, and then you run your compaction algorithm.
Mm-hmm. Do you want to try that?
Yeah. So this free node becomes just node.
Mm-hmm.
And you probably do need a next and a previous.
Yep.
Struct node. And you also need a bool. I guess they're ints in C.
Like for whether this particular thing is allocated or not?
Yeah. Well, you need some way to distinguish whether this is a free or not.
Mm-hmm.
Does this make sense or not?
So you're going to imagine you're keeping these lists basically in memory order. Like another possibility is you could have 2 lists, the allocated list and the free list. But you want to basically be able to take 2 free list entries that are next to each other, recognize that they're contiguous, and merge them back into one to defragment. Is that where you're going?
I have never implemented malloc before. Remember, I was a math major, not a CS major. And so I am just doing this off of assumption. But my assumption here from having seen Copilot spit out this with a free tag to it.
Mhm.
It was like, you could just do the same thing that we did in the GC and use this as a header to the allocation. So whenever you have a pointer or something, you just back up, the size of the header, and then you have your reference to your thing.
Mhm.
And so then you end up with one single list of all of your nodes, both free and not. And yes, you need to keep them in in-memory order.
Mhm.
But I don't know if that's a good way or not. That's just where I went from Copilot's implicit suggestion.
Yeah. So one thing you need to be careful of is you, let's say your pool is pretty full and you want to go find some empty space in your pool.
Mhm.
It's usually important to be able to index into the empty space quickly because that's what you need to do to allocate some space.
I
And so
see.
like a common strategy here is you keep 2 doubly linked lists, the list in order, and then you also keep a free a list of the free ones.
Yep. Okay. I also know that real allocators also have they have like small size pools. They like have different pools that they allocate from.
Absolutely. So we're doing the what we call the big pool. So for largish objects. And so I don't think we'll get to it in this episode. Maybe we'll do it next episode. We can do one of the pools for fixed size objects that are small, because then you end up like using a bit mask at the beginning to say which of the fields are occupied, and then because it's fixed size, you can just index into it really quickly.
Yeah.
But
Exactly.
you also
like,
need
things that are 8 bytes. You just like, yeah, fine. We need a whole bunch of those.
Mm-hmm. But it's also a common practice that once you have the like big squishy allocator, you use the big squishy allocator internally inside malloc to implement your pool, to allocate your pools.
Sure.
So you kind of need the big squishy allocator as like a bootstrapping step.
So you're telling me that this approach is going to make us sad because we're going to struggle to get to our freed, because we're going to have 1,000 used things and you're going to have to walk through 1,000 before you find your first freed thing every time.
I think this is good. I think we should do this approach, but we should recognize that this is a stepping stone that we're going to want to come back and iterate on when we look at performance. Like we will be able to do things that like a correct, reasonable thing with this structure. Like a fully featured malloc is very, very complicated, right? And so like whatever design we talk about, I can always think of, oh, here's something that design doesn't do well, and eventually you get something really super complicated.
Okay, so we're continuing with this structure of having a unified list.
Yep.
Okay.
And I'll just mention it while we're here. Like this structure is very large. Another thing that is important in malloc is we're going to compactify this. So instead of being pointers, these things being offsets, this bit gets folded into the size by slicing some bits off. But forget all that. We'll get there.
Yeah.
Let's do the big one for now.
Yep.
Okay. So now the pool is going to have our the node. Yep.
This is first.
Yep. And you want last usually too.
Really? So you can walk either way.
Yeah, it just makes everything nice and symmetric.
Okay.
Okay, so now we have to initialize our thing. So we have first, next.
The tools give you no help. You're just, you might as well be writing assembler. Oh, jeez.
Yep. Let's not do last. We'll just do first round. Okay, current is first. No first. So in this case, there will always be a first because we're going to keep entries. Okay. We don't need previous because we're doubly linked. The needed size is going to be size plus
size of node.
Yep. There's another way of doing it where you set the size to be the remaining size. So why don't we do that? So the size will be the one exclusive of the header. It'd be like the available size. Okay, then we don't need this. previous anymore. Next. If we run out of current, then we're sad. Okay. Okay. So in this case, we never have to do list surgery. We're just, while the current is less than size and current
It's not equal null.
Is free.
Oh.
Oh no, wait.
Is not free.
Well, why don't we do this way? If current is not equal null, we're going to walk, right?
Yeah.
Okay.
You just do while true, honestly, because you want to include the.
This is fine. We'll just do this.
Okay, fine.
Right. If current is free.
Oh, sorry, we're fighting each other. Go ahead.
Right. No, you go ahead.
Let me get back to true. Okay, well, true. Current is free. Current size is greater than size.
Yep. This is actually going to be plus size of.
Mm-hmm.
Okay.
If current is equal to null. Current null.
Okay. Any of this? Problem solved. Done. Allocator works. Not quite. So we may want to split the node, right? So if the size, current size is bigger than the size we need plus the size of struct.
Whoa.
I don't know if this code is right. We'll do this. Then we want to split the node. Okay. Yeah, this looks right. Here's our new node. The new node next is the current next. The previous is current. That's correct. The size is the current size minus the size minus the size of the node. Yep. The new one is free. Yep. The current node's next is new node. And the current size is size.
Good job, Copilot.
Yep. Good job, Copilot. That's amazing. Okay. Return this. Yep. Okay.
Why is this char star cast necessary?
Because we want to count in bytes.
When we
if we didn't do this, we would be counting in nodes.
Yep. Oh, yes.
I'm going to be pedantic and put this back here. And then just shove this out here.
Well, but then you have to, okay. Oh, I see. Which is fine because we don't continue. Yeah, that's fine. Okay.
Yep. Okay, so now we need to implement free. So free, now to recover the node, we have to
cast it to a char star and subtract the size of node.
Minus size of struct node.
Yep.
Okay.
Like we would put these in helper functions if we were.
Yep. And the most trivial thing we can do is we can say it's free. We did it, team.
Yeah, could compact, right?
Yeah, now compact. So compacting should be easy, right? We should say if node has a previous, previous, and the previous is free, we can compact the previous, right? And we could just say
compact the other way too.
Yep, but let's try to do this case first. So struct node previous.
You just fix up the previous as pointers. You don't have to do anything else.
It's size, right? So when you say previous, his size got bigger.
Oh
It's
man, there's just so much possibility for this all to be wrong.
oh yeah. So
Like you just have
so
one stray character somewhere in your whole program.
uh-huh. I mean, we could try doing it in C++. It's definitely possible. It's just there's you have different pitfalls.
No, it's
But
all fine.
yeah,
I wonder what this would
like
be like in Zig.
maybe we should have done an announcement at the top of the show. Do not try this at home. This is tricky stuff.
Well, that doesn't mean that we're going to be any better at it, but yeah.
Okay, and then we need to say previous next is node.next, and if node, yeah. Thank you, Copilot. Copilot helps.
I just remember like this was the beginning of my career. It was writing in C and C++, and like I just don't think we knew how bad it was, or I didn't know how bad it was then.
Okay, this is what Copilot thinks we should do to merge with next. It's like this: next is size plus equals, yeah. The nexts.
I see. Node is now previous. Yeah, fine.
This doesn't seem quite right.
That's nice.
Oh, I see. We're destroying next. So we eat next. Node is the one that's going to come out of this alive. Just that makes sense. Yeah. So our next is now his next, and if he has a next, then his previous is now us instead of them. Yep, that looks right.
Okay.
Should we try it? I think we have a correct implementation. It's perfectly correct. There are no bugs.
All right, let's write some tests.
Okay.
What are things we would expect? We like.
Well, it becomes hard to test. Like
Why?
Well, okay, let's try to write some tests.
What's hard to test?
Well, let's try to write some tests. Let's do it. So we're gonna say void star.
Like we may have to write some additional like helpers to reach inside and see how many,
Maybe we should make a thing that prints out the list.
Sure.
Dump heap.
And you want dump heap to just it's like walk the free list and print out the free nodes. Yes. Go Copilot, go.
You could do it, Copilot. I don't know how people wrote code without Copilot. It's amazing. The code's not right, but it's not wrong either.
Well, as we've discussed before, it just changes the job. You become a reviewer instead of a man page reader.
Okay. Should we try it?
Well, I'm just trying to review this code to make sure. Current.
It's close enough.
Current size is free. Yeah. Like you don't have to go look up. Well, is it
ZU?
Is it Z or is it F or D or Q? Which archaic thing did printf use?
Oh, we forgot that. We need to write void here because we're in C. Otherwise, it's a variadic function.
Okay, so this may stymie us here. Let's assume that this is just a VS Code problem and that the terminal will find it. The terminal has other opinions. Unknown type bool. What?
That's fine. We can include SCD bool. I think SCD bool.
Maybe it's just it's big.
No. Try it. We included SCD bool. I believe that will fix this.
What the hell is SCD bool?
SCD bool is like, okay, make bool sane in C for me, please. It's like SCD int. It's like give me the real integers with the numbers, like the sizes. So
I don't think this existed when I was.
No. It's a newish thing.
I love it. Oh my goodness, 2019.
Okay, so this should be start. Okay.
What?
Bool is
okay. Invalid type struct pool. Oh, I see you. Okay. Struct node where pointer gpool start.
Oh, we're seeing a star. Insert more stars.
Yeah. Okay. And then incompatible pointer type initialing.
Oh, we've seen a cast.
Cast.
Where was that?
Struct node pointer.
Yeah. Oh, then we need a parenthesis. Order of operations will blow our minds.
Okay. Okay.
Okay.
What am I going to do? Is that correct?
Well, let's maybe we should just print it out before we allocate anything. For the sake of our sanity's sake. Oh, you need to recompile.
Yes. Okay. Empty.
I think we're not printing out the first one for some reason. Why isn't it printing out empty? Oh, we need to call malloc. We need to initialize the heap. Let's just pull that into a separate function for now.
Most of this should get pulled out into a separate function, by the way.
Let's a init heap. Init heap, dump heap. Okay.
I mean, we could just call it init heap if needed, and then it would be. But yeah. Okay, init heap worked.
Okay, so let's try to malloc something.
And then well, you're only doing 100, but sure.
So that's not so good. Why did malloc not change our list? Oh, we need to call my malloc. Oh, we did call my malloc. Okay.
Well, what did it come back with? That'll be another thing to add. Oh.
All right.
Oh, sorry, I'm following you, which is part of my problem in life. All right, this. Save me, Copilot. What is it? I don't remember any current pointer. Is it just P?
Mm-hmm.
Okay. Nil.
Okay, that's not
explain. So what's going on?
We did something wrong.
While current is not equal to null.
Okay. If it's free.
And the size is greater than size.
Okay. Oh, we didn't initialize the pool to be free. We should say, we want you to be free. Go. The pool is full. Which we should actually see from our print.
There we go.
There we go.
Yeah.
Let's call malloc a few more times and see what happens.
Malloc something. This is progress in C and less. I don't know if you showed this already.
No.
Yes. There was progress in C in the last 30 years. What is this hot thing? Updating IntelliSense. Okay. We're getting towards the end of our episode here.
Yeah, but I think we have a working heap. We'll try freeing some things in a second, and then I think we should declare victory on like heap version 0.0.1. Okay, let's try dumping the heap here. What do we got? Yeah,
size. Yeah, that looks right.
Okay, so
let's free one.
Let's free one. Which one do you want to free?
I want to free the second one. Yeah, pointer one.
Pointer two.
Mm-hmm.
Okay.
Yeah, I mean, we're going to end up doing like a unit testing harness here. Oh.
I didn't have a semicolon. Is that why it's... Yeah, okay.
Yeah.
You want a pointer two, right?
Yep. And then you want to dump, and then you want to do pointer three and see if it... I mean, whatever. These are all things you want to like unit test.
But I think in the interest of...
Yeah, this is great. Also very visual.
Point of
Okay. What do we got?
So,
okay,
which was pointer 2? Pointer 2 was the second 100.
Mm-hmm. We did not free it.
Okay, so let's go look at our free routine. Oh, we didn't. Oh, node is free. When we did these merges,
Mm-hmm.
no, why did we not free it? Let's get rid of the coalescing code for now, right? Just to simplify our lives.
Sure.
So we're trying to recover the node and set its is free marker to true. Can we try that?
Did we correctly return? Yeah. Okay. So we didn't ever return the wrong one. This is the only place. Because we really need to like from user pointer to.
Oh, there's a char star missing there.
Where?
Right. This current is a node.
Oh.
Yeah. Okay.
Danger, Will Robinson.
Super danger. Try this.
Yeah, just that this means different based on the size of the pointer type.
We're gonna have to do a thing where we turn it into C++ and like take the knives away. Stop shooting ourselves in the. Okay.
Okay.
That's
so
right. All right. The first time we freed the 100.
that one. We freed that one.
Okay.
So we turn back on the coalescing code.
Let's see what happens.
For our grand finale?
The grand finale. Yeah, look at that. Oh, interesting. Is that right? Yeah, so it's 100 plus 210 ends up as more than 310 because we got the header back.
Yeah.
This is great victory. We have a working malloc. It's very dumb and very inefficient, but it does the thing.
All right. Work from RDE. I think we're 119 tonight.
Yeah, episode 119.
It works. See what this is. And it's published as simple malloc. Go us.
Go us.
Oh, my poor machine just hung.
Be free, allocations, be free. Yeah, we don't actually return the memory to the OS, but you know, we'll get there. It's more like a WebAssembly allocator, one might say.
Can you remove my screen? My production machine failed.
I sort of know how to produce the show.
There we go. My production machine got down to 3% power, and it was like, nope, I'm sorry, I can't do video anymore. This tab is hung.
We should put this in the show. Yes. We should get further than I thought. I didn't think we would actually get like block coalescing. That's a pretty.
Well, I learned this that there are an episode we could do on malloc should we choose.
I think people built their whole career on malloc. Like it's that. Like.
Well, when you write it in C, you really do need a person who's trained up for 30 years to be able to understand it. Anyways, this was great. Thanks all for coming by. Any further thoughts?
No, I think we'll see you next week.
See you next week.